Hello, thank you for joining me. My name is Martin Fuller. I'm an engineer with the Microsoft Advanced Technology Group. This presentation is an update on variable rate shading on the Xbox Series consoles. So this talk will cover variable rate shading on Xbox and what we've learned so far with first-party titles leading the charge. We have some tales from the trenches from Gears 5, some early work with Unreal Engine 5 and Nanite, and finally Doom Eternal. We will then talk about some best practices for the Xbox hardware specifically before wrapping the talk up and giving some conclusions. So, variable rate shading, the story so far on Xbox. The Xbox Series consoles are the very first consoles to feature variable rate shading, and as such adoption has been relatively slow, which is to be expected when a lot of effort is going into getting the Gen 8 consoles to perform. There were some launch titles made some limited use, particularly rendering particle systems at say 2x2 rate. Where things are getting more interesting is that titles are now beginning to experiment with the screen space shading rate image, which on Xbox is a shading rate selection for every 8x8 screen tile. So the headline takeaway from those titles that have adopted Tier 2 VRS with the screen space image is that it's fairly common to get between a 10 and 50% reduction in overall frame time. That's on Xbox Series X. This is very much content dependent. There are outliers. You might save less than 10%, you might save more than 15%. But the gratifying thing is that what we're told by real games is that the win you see from variable rate shading is higher in worst case scenes. Xbox Series S, what we see there is that the benefits are in fact smaller. And this is because at a lower resolution it's harder to use the coarser rates. So you might expect Xbox Series X to benefit more in a resolution mode than a frame rate mode, but typically we haven't seen a loss on Xbox Series S. We normally see a win of some degree, just not as large as Xbox Series X. So people who have been following variable rate shading will know that as well as the kind of finer rates, 1x1 down to 2x2, variable rate shading also supports 4x rates, and what we found with experience is that these are generally not worth it. They are very hard to use without seeing a quality issue, particularly on Xbox Series S. It's much easier to hit fixed function hardware limits because you are making the pixel shader do less work, so you have the fixed hardware on the front end and the back end of the pixel shader. It's slower to compute the shading rate image because you have more options. So in our experience so far, we find these are not really worth the effort to try and use a 4x rate. So perhaps counterintuitively, the other message we've had from early titles is that variable rate shading actually increases quality. Whereas you would think that running the pixel shader less often would decrease quality. The savings from variable rate shading typically allow the title to automatically increase resolution. So what this is doing is it is increasing the resolution where you really need the detail, where you're running at full rate or full rate in a single axis, and where you don't need the detail you're running at a low rate. So the overall perceived image quality increases from variable rate shading. The other thing I mentioned briefly is that variable rate shading tends to give a bigger win in the worst case scenes. So what this means is that this is where we are processing things that we would traditionally consider to be very expensive and we would use in moderation. So this would be motion blur, depth of field, bloom, heat haze. These are all kind of blurs. It's always been a bit of a disappointment that making things more blurry is more expensive. Of course, we have a natural phenomenon that are quite diffuse by their nature. So this would be clouds, atmospheric scattering, God rays, fog, that kind of thing. We also have surfaces with subsurface scattering. They tend to be extremely diffuse. Again, you would use some kind of blur pass, so this would be skin and snow. And then of course we have particles, particularly if they are properly receiving light. Shadow maps, they can be extremely expensive. Variable rate shading can really help here, again because particles are typically quite diffuse. So this is really good news for being able to afford more of these type of seriously expensive effects. So one of the first questions that we get from developers about variable rate shading is, if I'm generating a screen space map based on last frame, does it matter about object movement and camera velocity? And in theory, you could use object movement and a velocity buffer to improve the shading rate determination for your current frame. So far, in fact, real titles haven't done this. It hasn't proved to be necessary. And if you did so, you would have problems, of course, with disocclusion. This object has moved, it's exposed something behind it. What shading rate should we pick for this? Should it be full rate just in case, or should it be? Can we get away with a low rate? And the reason that it doesn't matter particularly is that if you pick a coarse shading rate when you shouldn't have done, you're only getting a low resolution result. You're not getting a result that's wrong. It's not like checkerboard where if you pick, the wrong result to hole fill, that you're damaging the object's silhouette. That doesn't happen with variable rate shading because coverage is always full rate. It is only the resolution of the triangle interiors that is affected by your shading rate. So the other question we get, of course, is what about camera cuts? And so this is where you have a new frame and your previous frame has no relationship at all. You're building a shading rate based on your previous frame, and it's completely unrelated to the new frame. You could detect this and set the whole screen to full rate perhaps, but again, real titles so far haven't done this. They have lived with the shading rate from the previous frame being completely incorrect. And this gives a one frame error where you've picked the wrong resolution possibly for every screen tile. But this is far less of a problem than something like checkerboard, for example, where on the first frame you can see all the sawtooth patterns. There's no temporal history. Again, with variable rate shading, you have perfect coverage, and it is only the resolution of triangle interiors that is varying, and perhaps in an incorrect way. The main thing is to make sure that if you picked a low shading rate, that this can recover for the next frame. And really, this is extremely simple. All you have to do is make sure that your kernel that you're using to determine the shading rate is wider than your coarsest rate. And we've done many experiments to show that this will recover the shading rate image in a single frame. And in fact, this is what real games have done. Some early papers on variable rate shading discuss this idea of foveated rendering, where you might decrease the shading rate near the edges of the screen. And we have seen a form of this, which is a simplistic version where you simply set the safe area of the screen to a low rate, and you don't in fact compute the rate for those tiles. So exactly how large this safe area that's at an enforced low rate is might depend on which console you're running on. So for the higher 4K resolution on Series X, this might be 2 tiles. Say 1440p resolution on Series S, this might be a single tile. And the optimization is quite simply to memset the entire surface to 2x2 rate, and then run a compute shader just on the interior tiles. And the big advantage of this is not only reducing the amount of work this compute shader has to do, but the compute shader doesn't have to handle the boundary conditions at the edge of the screen. Of course, things get a little bit more complicated for the majority of titles that implement dynamic resolution scaling. So in this case, we can still mem set the entire surface to 2x2 rate, which would be the green tiles in this case. And the interior, we're running a compute shader on the 5x5 tiles that is calculating what the shading rate for these 25 tiles should be. And then in red here we have the bottom and right hand boundary. Now ordinarily we wouldn't touch these, the compute shader wouldn't be running for them, they'd be set to 2x2 rate. But whenever we change resolution, we're going to have to set these to 2x2 rate. So for these red tiles, we only process these on a resolution change. And in this case, the most optimal way to do that is just to increase the size of the dispatch by an extra column and an extra row. And then the shader detects that, yes, we're off the tile we're processing is outside of this 5x5. Therefore, we just mem set it to 2x2 rate. The other issue we have to deal with VRS and dynamic resolution scaling is, of course, the previous frame may be a different resolution to the current frame, so we need to be able to handle this. What some titles have done, early titles have done, is they've actually rescaled the shading rate image, and this has worked on some occasions. In other titles, we've seen a performance or a quality problem with this. And the simplest way to explain this is to think about a really very small render target. So let's imagine it's just 2 tiles large, so it's 2x1 in tile space. And the left-hand tile is running at full rate and the right-hand tile is running at low rate. And if we change resolution the next frame and we end up with 3 tiles, so 3x1, and the left-hand tile again is full rate and the right-hand tile again is low rate, what should the middle tile be? And the problem here, you have to make a decision. It has to be something. So you could take high rates, which would be conservative, so possibly that's running at a higher rate than it needs to be and we're losing performance. Or you could you could set it to low rate and potentially the quality is lower than it should be. But again, only for the single frame. So the solution I came up with was to, instead of rescaling the shading rate image, is to bilinearly sample the previous frame. And that can be done all in one pass. There's no rescale shader as such. So with thanks to 343 Industries and the Halo Infinite team, I can show you exactly what this looks like. The first thing to note is the debug colors, and of course everybody chooses different debug colors. In this case, 2x2, the coarseness rate is denoted in yellow, and we have the half rates in red and green. And in the left-hand image, we have a resolution change in both cases here, a decrease in resolution. And in the left-hand image, we're choosing the lower, when there's a decision to be made, it's choosing the lowest rate. So this is favoring performance. In the right-hand image, there is no rescaling of the shading rate image. This is just a single pass, single shader. So it is in fact faster than producing the left-hand result. And here we're doing a bilinear resampling of the previous frame, which is at a different resolution. So not only is this shader faster, or the process faster in the right hand image, it's giving a higher quality end results that better matches what we expect to render this frame. Another choice developers have is exactly which buffer to use to derive the shading rate from for the next frame. And for the highest quality and the highest performance, we recommend that you use a buffer from your internal resolution, which may be lower than the final output resolution. Ideally, this buffer would be after you've done your post-effect blurs, so particularly any camera motion blur, any depth of field, any strong blooms, because these will all be making the image more diffuse, removing high frequency detail, therefore allowing us to use a coarser shading rate next frame. But ideally we would use this buffer before the user interface has been rendered into it, because we don't want the user interface elements to be increasing the shading rate of the 3D scene behind it due to the injection of some high frequency detail in the final image. So somewhere where we've done quite a lot of research since the Generation 9 consoles launched is best practice for variable rate shading and high dynamic range. So this is kind of interesting and new. So ideally the shading rate computation should be done in perceptual space, and this is because we really care about how the eye perceives light more than we care about what's going on in linear values. So your eye is good at picking up things in dark areas, so we would like some to boost the shading rates in dark areas compared to our linear signal. When we get into really bright, oversaturated areas, we care about the shading rate less. We'd quite like to reduce the shading rate in blown out bright areas. The problem here is that the source image for determining the shading rate is often not being tone mapped. So this might be because the tone mapping has been done by the hardware. It might even be done by the television itself, and it might be done not at the internal resolution but on upscaling to the output resolution. So the tone mapped image may not be available to you for generating the shading rate image. So the obvious first thing to attempt here was to apply an existing tone mapping curve, and my first choice was to use Reinhardt for a few reasons. Firstly, it's very cheap. It doesn't have a tone mapping toe. Secondly, it's a well-defined curve, and this will do pretty much what I want in reducing values in the bright area. The optimization here is, of course, to operate on just luminance, not each of RGB. And the reason for this is that the shading rate determination that we've been doing and Real Titles have been doing is on luminance only, which has proved to be highly successful. So we're ending up with one divide instead of three. As I say, this work with HDR and VRS is extremely new, and I'm very grateful to Philip Hammer from IdTech, who was prepared to implement some of my ideas so that we could see it with real-world content. Although I should stress that Doom Eternal has not shipped with these experiments. So these are the only images available with the various curves I'm going to talk about. So here's a test image from Doom Eternal with a demon with a particularly large flamethrower and a great deal of HDR content. So here we have the shading rate image from Doom Eternal, which as usual uses different colors for its debug. So here the lowest rate 2x2, the one we're really interested in, is dark blue. High rate is red. And then the two half rates are in green and cyan. And we can see on the left hand image where we're just using linear Loomer, we've got a high rate all over this HDR effect. And on the right, when we've applied Reinhardt Loomer, we have a significant reduction in shading rate. A huge amount of the high rate has reduced. And if we overlay that shading rate image over the original image as a transparency, it's perhaps a bit clearer exactly how Reinhardt Loomer has benefited its scene in reducing the shading rate, which is of course applied to all the geometry behind this effect. So Reinhardt is interesting. It's dealt with values in the HDR range in the way I'd hoped. But what it doesn't do is it doesn't do the other thing I mentioned, which is increase the shading rate in values that are less than 1 in the SDR range, particularly in much darker colors. So using a few graphs here, we have linear is in orange, we have Reinhardt in green, and we can see this zooming off, it never quite reaches 1. The next graph I decided to attempt was simply using square root. It's fairly cheap, it's just 1 instruction, and this will reduce the value in the HDR range, though not nearly as significantly as Reinhardt, but it will also boost the shading rates when less than 1 in the SDR range. So here again, a scene from Doom Eternal. From left to right, we have the source image, which is fairly dark, except for we have this bright HDR source in the light and in the reflection of that light in the gun. So again, we have linear luminance next to that. Then we have Reinhardt, which again there's relatively little difference, except that it's reduced the shading rate around the light. And then finally we have square root of the luminance, and we can see here we have a big change. So we have a lot more half rate and full rate in the darker tones. So again, this is what I was looking for, though it is, as we saw from the graphs, less effective at reducing the shading rate in the HDR range. And square root of Loomer is in fact what Doom Eternal shipped with. They were very happy with this increase of shading rate in the dark tones versus linear luminance. However, it occurred to me that we could do even better than Reinhardt Loomer or square root Loomer. And what we have here is we have several desirable features. So Reinhardt Loomer is doing really well at aggressively reducing shading rate in the HDR range. However, for the square root, there's 2 properties I like here. Firstly, that we have this crossover point at 1.0, and then also we have this property that shading rate is increased in the SDR range. It didn't take me long to come up with a new curve that satisfied all 3 of these desirable features. This was simply a doubling of Reinhardt Loomer, as can be seen here in the blue curve. So we have this crossover point at 1.0, and in the HDR range, which is above 1.0, we see a reduction in the shading rate that's more aggressive than square root of luminance. In the SDR range below 1.0, we also see this increase in shading rate. So we'll see what that looks like. So again, source image from Doom Eternal with some HDR light sources, this time also including a lightning bolt. So here we have the 4 different shading rate images. We have linear or just Loomer in the top left. We have Reinhardt in the bottom left. You can see here the main difference is in reducing the shading rate on the lightning bolt and the light source, but there's basically no increase in the SDR range. At the top right, we have square roots of luminance, which again is what Doom Eternal actually shipped with. Here we can see that there's some reduction of the shading rate in the HDR range, so on the light and on the lightning bolt. But we do have a big increase in shading rate in the SDR range. And then in the bottom right, finally, we have the 2x Reinhardt Loomer. And this I think is the best option, and in fact Philip from IdTech agrees. This may well be used by future titles. So we have a reduction in the HDR of the lightning bolts and the light compared to regular linear luminance, and we have an increase in shading rate in the SDR range, but not as aggressively as square root. So I think this gives the best result. So here we are again with a transparent overlay of the shading rate, and this is linear luminance. We can see obviously high rate on the HDR sources, but relatively little the rest of the scene is anything other than 2x2 rate. Most of the scene is being rendered at 1 pixel shader amplification for 4 pixels. And here is the same scene, exact same input with 2x Reinhardt Loomer. We can see here there is a reduction in the HDR range, which we want, but there is more detail in the SDR range is being picked out, which is exactly what we wanted. The main takeaway is that there are two controls that you can use for shading rate selection. The first is the curve that you apply to mimic the toner mapping. You can of course roll your own. I strongly recommend that you at least give 2x Reinhardt Loomer a trial. And then there's the cutoff values in what is the delta in luminance at which you decide that you are going to go for a high shading rate in each of the X and Y axes. And of course, you don't have to settle with just one setting for your entire title. You can have different VRS modes for performance, for quality, and maybe different shading rate images for different post-processing passes. You can perhaps even be more aggressive when the GPU comes under load, kind of very similar to dynamic resolution scaling, except that you're also tuning the VRS cutoff values. So the single largest reason why you might get a high shading rate selection when you don't need one is due to depth discontinuities. So the simplest way of explaining this is that you have a foreground object that could be rendered at a low rate, and in the same screen tile you have a background object that could also be rendered at a low rate. But in fact these two objects have a very different luminance value. And this is causing the shading rate determination to pick a high rate when in fact you don't need one. And the simple way to fix this is to take into account depth discontinuities to disallow any components of your kernel where there is a large depth discontinuity. Unfortunately, this is not free. With loading depth into our shading rate determination shader was a very significant cost. It almost doubled the cost of the shader. However, there's what I found was a very big optimization, which is that when you have this problem of depth discontinuities, it tends to produce a 1:1 shading rate, the highest rate. And the reason for this is that and why you don't get a 1:2 or a 2:1 is that your depth discontinuity is very rarely exactly vertical or exactly horizontal within that screen space tile. It's normally some kind of a diagonal, which will then cause a high rate selection in both axes, giving you 1:1 rate. So a really nice optimization here is to say, right, we're only going to load depth for screen space tiles which produced a 1:1 rate. So we do the shading rate determination on luminance first. If it says 1:1 rate, then we load the depth, and then we do shading rate determination again, but this time testing depth. And this was quite a significant win. How much, or when it is, of course, depends very much on your content. How many 1:1 rate tiles were you getting, and how many have you demoted to a lower shading rate as a result of testing depth discontinuities. So our original variable rate shading sample for Xbox Series consoles used an 8x8 thread group size when determining the shading rate for each tile. Subsequently, I found an optimization. This shader was basically vector memory limited, which is to use a larger thread group size, 16 by 16, and then I'd have each of the half the threads, which works out to be 162, would each load 2 colors, convert it to luminance, and store those into an 18 by 18 local array. And what this did was it chopped down the number of memory operations to 81% of what I had been issuing for a 8 by 8 thread group size. And this gave a much better balanced shader. Instead of being vector memory limited, we're pretty much level now between vector memory and vector ALU. So this was all very well until I added depth testing. And the issue here is that a single thread group is processing 4 screen tiles. So mentioned on Xbox Series console, each one is 8 by 8. So again, if we've generated a high rates tile and we want to do depth testing, we're going to need to load 10 by 10 depth values, but for any combination of the 4 tiles. This gets quite hard to handle in an optimized way. So in my experience, it's actually, if you are going to do depth testing, you might prefer the 8 by 8 thread group size. There is in fact an even better solution, and that is that you very likely have an existing pass that is doing some kind of edge determination already. It's probably something like temporal anti-aliasing. It may well be using motion vectors. It's probably loading depth. It's doing color clamping. And in fact, a lot of this work is extremely similar to shading rate determination. You're looking for discontinuities. So it's very likely that you can exploit this shader to output a shading rate image for the next frame, extremely low cost, and with depth discontinuity testing built in. And this will be better than using a standalone shader such as our samples.
Thanks for all the great VRS background, Martin. I'm Chris, one of the engineers on the rendering team at the Coalition, and I'll be talking about our experience shipping Tier 2 VRS in Gears 5 for both Xbox Series X and S, as well as PC. For the purposes of this talk, I'll just be doing a very brief overview of our VRS implementation. If you're interested in more in-depth optimization tips and some of the bugs we encountered, I highly recommend you watch our GameStack live talk we did on VRS. Additionally, we also have a DirectX developer blog post that goes over some of our implementation with additional performance numbers. So why implement VRS? For us, the primary benefit was that the performance savings in VRS allowed for an increase in dynamic resolution scaling. Thanks to the extra control allowed using Tier 2's screen space VRS texture, we were able to ensure that the reduced shading from VRS never becomes perceptually noticeable. Our implementation uses VRS across the entirety of the frame. The most obvious usage was applying it to base pass, translucency, and lighting. However, we also applied it to full screen effects such as SSR and SSAO, which is actually where a majority of our VRS wins came from. And finally, we also applied it to SSGI, our screen space global illumination pass. SSGI is interesting because it's a compute shader, but because the VRS texture is also just a GPU texture, you can read from it like any other SRV and emulate VRS behavior in the compute shader. Here are some of the performance numbers on the Xbox Series X. The numbers are taken with the resolution locked to 4K for both VRS on and off. In practice, we use dynamic resolution to ensure the cinematic runs at a smooth 60 frames per second. And in this case, VRS allows dynamic resolution scaling to go from 83% all the way up to 92%. Cinematics are a great case for VRS because the heavy use of DOF allows for VRS to go fairly aggressive in the background with no noticeable visual impact. I love this particular example because the bump in resolution makes a very noticeable difference, obviously with textures, but it's even more noticeable in the alpha mass material like Kate's hair and the fur on her armor. Notice in the performance numbers that the savings for most of the passes are quite good, but SSR and especially SSAO are a standout, with SSAO running over twice as fast. Our implementation of VRS is fairly straightforward. We have an edge detection compute shader that takes in the output of the previous 4K frame and outputs a VRS texture. On the next frame, we rescale the VRS texture to match the requested scaling from dynamic resolution scaling. We also do reprojection in this step. We could have done the reprojection and the edge detection shader, but doing it at 4K ended up being too expensive, and the approximate reprojection at a much lower resolution proved to be good enough. And then finally, the easy part is simply binding the VRS texture to any of the passes you want VRS applied to. I wanted to call out that we spent a lot of time thinking about where to do the VRS texture generation. We settled on doing it at the end of our post-processing chain. In terms of performance, doing the VRS texture generation at the end of the frame, and in particular after the TAA upscale, means we're always reading in a 4K texture, even if dynamic resolution scaling is below 4K, which can seem a little silly. However, enabling VRS to catch areas of heavy blurring from DOF or motion blur was just too good to pass up. In addition, doing VRS after TAA became important because subpixel geometry or specular highlights can pop in and out between frames. And so running the VRS texture generation before TAA might cause you to mark areas for coarse shading when it really shouldn't be. One thing we did find when using VRS across a wide variety of passes is that not all effects degrade equally when reduced to coarser shading rates. SSR, for example, on glossy surfaces can be quite noticeable if VRS is applied too aggressively. Most of the other passes, however, could get away with surprising amounts of VRS. To handle this difference in VRS sensitivity, we ended up outputting two different VRS textures, the main VRS texture and a more conservative VRS texture. The cost of outputting the second texture was largely negligible since we're just reusing the results of the edge detection shader but comparing against a higher threshold value. While a bit of a tangent, I also wanted to talk a bit about relaxed cone step maps, which our tech artists relied quite heavily on in Gears 5 and actually paired quite nicely with VRS. And while Gears 5 didn't use ray tracing, it's also worth calling out that relaxed cone step maps also pair well with ray tracing. So what is relaxed cone step mapping? Relaxed cone step mapping is based on an NVIDIA paper in GPU Gems 3. I won't go into the details since the paper is actually quite good, but at a high level you can think of it as an accelerated version of parallax occlusion mapping that you can use if your height map is static. By baking visibility information in the form of a cone angle, you can accelerate the ray marching portion of parallax occlusion mapping. Relaxed cone step mapping fundamentally allows you to shift your geometric detail from triangles to textures. This is great for VRS because as triangles approach pixel size, the efficiency of VRS starts to drop. You can also get good memory savings because you benefit from BC texture compression. The memory savings are even bigger for ray tracing where, unlike the triangle representation, you can share the texture between the raster and ray tracing pipeline. Finally, the relaxed cone step mapping performance can be tuned with a fairly simple knob. Our implementation would take a configurable amount of steps, with the amount of steps dropping as the geometry got further from the camera. For scalability, we had a quicker drop-off on low-end platforms and a longer drop-off for high-end platforms. For something like ray tracing, you could also tune this per effect, such as having a more aggressive knob just for ray tracing AO or shadows, or even just skipping the ray march completely. Here's an example of a snowy floor plane with relaxed cone step mapping off. As you can see, there's some detail coming from the normal map, but otherwise it's quite flat. And here's with relaxed cone step mapping on. Here's another example from a starting level in Gears 5. Again, the rocks are getting some detail from the normal map, but it's still quite flat. And then here's with RCSMs on. On the top right, you can see an example of what the RCSM texture would look like for this geometry. One last note on relaxed cone step mapping that I wanted to call out was the ability to modify the scene depth. However, rather than modify the scene depth directly using the SV depth modifier, we stored the depth modification in the G buffer. There's two reasons for this. The first is that using SV depth will disable VRS compatibility with the relaxed cone step mapping material. The other is that this gets around a performance issue where modifying the depth in the base pass would require us to run the RCSM logic twice, once in the depth pass and again in the base pass to ensure the depth values match up. Instead, we run a full screen pass after our base pass that consumes the G buffer and outputs a modified depth buffer. This modified depth buffer then later gets used by our contact shadows. An example, here's a terrain from the Gears 5 Hive Busters DLC. It has relaxed concept mapping enabled on the ground terrain, but contact shadows and the depth modification have been disabled. The geometry looks quite good, but on the bottom right you'd expect a little more self-shadowing when so much of the ground is protruding out. And here's with both contact shadows and depth modification enabled. As you can see, it really helps ground the relaxed concept map and make it feel like real geometry. Okay, so we've talked a good deal about Gears 5. I wanted to take some time to talk a little bit about the future for us, the Coalition, which is of course Unreal Engine 5. In 2021, we showcased our Alpha Point demo at GDC, which was a tech demo created to help us get more familiar with the exciting new tech in UE5. We've also ported our VRS implementation from Gears 5 into the Alpha Point demo, and I wanted to briefly talk about what we found. Interestingly, what we found was the best use case for VRS was actually Nanite. It's a bit hard not to have heard about Nanite at this point, but in case you haven't, it's UE's new virtualized geometry system that lets you efficiently render geometry with ridiculous triangle counts. Our application of VRS is not actually on Nanite's rasterization itself, which is quite exotic and uses tricks like compute shader rasterization and UAV atomics. That would not be trivial to make VRS compatible. Instead, we apply VRS to what Nanite calls the emit gbuffers pass. The emit gbuffers pass is where it essentially converts Nanite's visibility buffer into gbuffers and is the equivalent to the base pass for non-Nanite geometry, sort of. We'll talk a little more on the technical details in the next couple of slides, but in terms of performance, we saw the performance of this pass go from 1.09 milliseconds down to 0.73 milliseconds, which is a nice 33% speed up. I should emphasize that this is a technical demo and not a shipped game, so the content is not 100% representative and hasn't gone through the full gauntlet of tech art scrutiny, but it is worth calling out that we are using the same quality VRS knobs we used for Gears 5, so it is a glimpse at what we could expect. This is a screenshot of the Alpha Point demo with VRS off, and this is with VRS on. If you look at the texture and geometry detail, I wasn't really able to detect any differences. There are some splotchy changes in the lighting, but these are a separate artifact of Lumen unrelated to VRS. So what's really interesting is that on Gears 5, the base pass tended to have the lowest VRS perf gains compared to other passes like translucency and screen space reflections. Below is an example of a scene from Gears 5 on the Series X where we are getting a 3.8% performance boost, which is not awful, but it's also not 33% faster either. The perf gain from VRS is quite scene dependent, and in cinematics we did see a hefty win from VRS, but we never really saw more than a 5% perf increase from our base pass in gameplay. So it's worth asking, why is there such a big difference between Gears 5 and Alpha Point? The answer comes down to the difference in how normal deferred rendering is done versus Nanite. So this is an oversimplified diagram of what Unreal Engine 4's base pass would look like using traditional deferred rendering. Your base pass shaders take in a whole bunch of geometry as inputs to the vertex shader, and the pixel shader outputs gbuffers. What's worth emphasizing here is that the logic that converts the geometry into visible pixels is also slammed together with the logic evaluating Unreal Engine's material graph. So all that is done in a single shader, which has some implications as we'll see later. Those gbuffers then get passed along to lighting and go along their merry way to making a nice little picture. So this is another oversimplified diagram, but this time of a small slice of Nanite that we're interested in. If you're familiar with visibility rendering, this is a flavor of that. Nanite takes your whole scene of geometry, ignoring all material information, and rasterizes it into a visibility buffer, which contains far less information than you'd see in a gbuffer. At the end, you get a small amount of information that boils down to depth, material ID, and triangle ID. After that, we then do a emit gbuffers pass, which I also refer to as the base pass. This pass consumes the visibility buffer and issues a full screen draw call per material. The key difference from the deferred rendering base pass is at this point there's no geometry being passed to the vertex shader, just a full screen quad. Some clever depth stencil tricks make sure the material being drawn matches up with the material ID in the visibility buffer. That base pass outputs a G buffer, and from then on, the rendering path is identical to deferred rendering, where the lighting takes that and goes and makes nice images. So I've broken down the two approaches again here, but if I had to fizzle it down to one thing, the difference is that the material shaders in deferred rendering are operating on a high fidelity mesh, whereas in Nanite, you're working off a full screen quad. This has big implications for VRS. VRS has diminishing returns as triangles get smaller in relation to screen resolution. With Nanite, because we're working off a full screen quad, VRS shading rates aren't throttled by some of the pesky triangle edge limitations that can hold back deferred rendering on these dense triangle meshes. One useful metric to help understand VRS efficiency with pics on console is average shading rate. A value of 1 means full resolution and a value of 2 means half resolution. The base pass in Gears 5 tended to average around 1.2, whereas in Alpha Point we were seeing an average shading rate of 1.4. Because it's a different scene, this isn't apples to apples, but I rarely saw Gears 5 budge from that average of 1.2, even in the very dark scenes, so the value of 1.4 is still significant regardless. Again, I do want to stress that Alpha Point is a tech demo and not shipped content, but hopefully this data still helps illustrate why we see so much of a larger performance win. And that's all for me. I wanted to give a big thanks to the amazing team at the Coalition, and special thanks to Ian Wong, who did all of the relaxed concept mapping implementation and innovation work for Gears 5. And then also a thanks to the rest of the Coalition rendering team who helped in some shape or form with the VRS implementation.
Thanks, Martin, for giving us the chance to talk about the VRS integration in Doom Eternal. My name is Philipp Hammer and I'm a senior engine programmer at id Software. This is a rather practical part of Martin's presentation about our own VRS integration. For example, I'll talk about the savings we've seen and some of the issues we've addressed. The integration of VRS was part of our native Scarlet update for Doom Eternal that came out with the free next-gen update in June. The update adds ray-traced reflections, a 120Hz mode including 120 frames per second rendering, as well as several quality and resolution improvements. Our focus was on delivering consistently stable frame rate while maximizing resolution and image quality. We also tried to keep dynamic resolution scaling at a minimum, which should only kick in during heavy GPU load such as combat. So this is one of the few cases where we actually drop resolution scaling. Therefore, it's a great example for our VRS integration. Here you can see a debug overlay with the Tier 2 VRS shading rate image. Each 8x8 tile stores an integer representing a shading rate value, which is then selected for rendering and eventually reduce the amount of pixel shader invocations. The red tiles representing a 1x1 shading rate, so every pixel shader is invoked. Those tiles are rendering without any VRS benefits. The green and cyan tiles are running with a 1x2 and 2x1 shading rate, reducing the vertical and horizontal resolution by 2. The blue tiles representing a 2x2 shading rate, showing the largest savings by reducing the resolution on both axes. As mentioned, this is an extreme case measured in balanced mode with an internal resolution of native 4K on an Xbox Series X. VRS turns out to be more effective with higher resolutions. We've seen gains on our Lockhart modes as well, but not as prominent as in 4K on Anaconda. In ITAC 7, we use forward rendering for all object rendering, and we apply VRS on the opaque and blend passes. Even in regular, less problematic scenes, we see a good savings of around 5 to 10% GPU time, giving us headroom that we can use for other things. In some scenarios, like the one from the last slide, we see an even bigger improvement of sometimes up to 20 to 25%. We need to take every optimization into account that is available by the hardware. This is important even for an already well-optimized game like Doom Eternal. For example, our 120 Hz mode halves the GPU budget from 16 milliseconds to 8 milliseconds, which isn't really much. We see those frame time peaks usually in particle-heavy scenes, such as this combat scene. As expected, VRS shows the highest gains here, also because the tile classification will likely select a 2x2 shading rate for the sections with a low frequency particles, such as flames or smoke. As mentioned before, we are using Tier 2 VRS with a single shading rate image for both the opaque and blend passes. We found that forward rendering is a great fit for VRS in general, since the most expensive operations, such as lighting, decals, and texture sampling, are done during object rasterization. The shading rate image is generated from the raw rendered frame right after the blend pass, but before any user interface rendering or post-processing. The shading rate classification is done with the common approach of a Sobel filter that finds luminance discontinuities in both X and Y directions in screen space. The shading rate image is then bound to the opaque and blend passes in the subsequent frame. Our pre-Z pass doesn't use any VRS currently. We might look into that in the future, but we are not expecting savings anywhere near what we see in the opaque or blend pass. Here's some basic advice, but important to remember since it's easy to overlook or break during development. VRS will silently be disabled under certain but rather commonly used conditions. First is an easy one. Don't use the interpolated depth value from the built-in intrinsics SV position, but manually interpolate the position from the vertex shader and do the perspective divide in the pixel shader. Second, using SV depth or SV stencil ref will disable VRS for that shader. Probably you don't want to use it anyway since it disables optimizations like early Z or high Z as well. Consider moving that to a separate pass if you really need it. In general, regularly check VRS counters and PIX GPU captures. If the average VRS rate is 1:1, it might be worth checking the shading rate image in that region if that's really the case. VRS really worked without any major issues or perceptively visible quality losses, but we identified some corner cases where Tier 2 VRS simply wasn't a good fit. If you look at this World UI screen with moving scan lines, you see some blocky patterns showing up that are not intentional. Looking at our debug view lets us see the underlying issue, a temporarily unstable tile classification. That means each of the 8x8 tiles is assigned a different shading rate every frame. The VRS classification algorithm is fed by the previous frame image where VRS was already applied. The animating high-frequency scan lines will in this case lead to aliasing and wrong shading rate classification. The fix on our side was rather quick and easy. We tag individual objects or classes of objects and don't use the shading rate image at all. In our case, we override the shading rate image by forcing a 1:1 shading rate using the Tier 1 VRS API for all World UI objects. Last but not least, some more general and quick performance advice. Don't leave any optimizations on the table. Use each specialized hardware or software available on your platform. On Scarlett, use VRS or you'll spend GPU computing power on pixels where you don't see it. Also use async compute wherever possible to saturate your shader waves as much as possible. For example, overlapping compute post-processing with depth prepass or shadow rendering of the next frame is a good candidate for that. Simulating GPU particles or other non-graphics compute tasks can be offloaded to async compute as well. Here, it's worth hand tweaking shader wave limits of graphics and compute pipes to balance async loads in an optimal way. In our case, we can tweak wave limits during runtime and directly assess the overall GPU frame time. Especially on Scarlett and Durango, consider using the dedicated DMA engines for async clears, if they're not already busy with something else. clear render targets early on the asynchronous DMA queue and synchronize the graphics pipe where the actual clear should take place. Consider that the full screen clear can sometimes take 1/4 milliseconds, and you can do it almost for free if done right. DMA queues contend for bandwidth, so optimally kick the clears in low bandwidth areas of the frame. Check pics to find good spots for that. Also tweak your shaders for register usage and occupancy. This was important on GCN and still is on RDNA architectures. For example, use Shader Model 6 wave intrinsics and also the platform-specific intrinsics. Experiment with the Scarlett-specific shader compiler switches, for example, to enforce VGPR limits. This way, you can massage DXC to generate different assembly and possibly improve your shader performance. These are obviously not universal advices, but you can improve your shader performance quite a bit with that. So that's it. Thanks for listening. And as always, this is a group effort and wouldn't be possible without a great team. Therefore, thanks to the ITTech Engine team and also thanks to Martin for having me as part of this talk.
Thank you to Christopher and Philip for sharing details of their implementations. Very interesting to contrast between a fully deferred title in Gears 5 that got the majority of its win from applying VRS to post passes, deferred passes, and Doom Eternal, which is what you might call a semi-forward renderer, where the majority win from VRS actually comes from that forward pass. So moving on, just to round off the talk with some specifics for Xbox Series consoles. Of course, the theory of 2x2 rate is that we are processing the pixel shader just once for 4 pixels, and therefore we should be able to get a 75% reduction in the time taken, assuming we are pixel shader limited. And of course, one of the first things we did when we actually got Xbox Series hardware was to test this. And the good news is that we can nearly get that 75%. We can get to 74% plus change. So we're pretty close to the theoretical limit on savings. It is also possible that we can be limited by fixed function hardware. And this can be the front ends, which means before the pixel shader. And this could be in the rasterizer scan conversion, or it can be in the depth block. And this could be dependent on triangle sizes. Or it could be in the back end, so it could be after the pixel shader. So this could be either the RB units or bandwidth being a bottleneck. And we can see both of these in pics. So perhaps the trickier of the two bottlenecks to identify and fix is the front end bottleneck. The back end one, we have a PS export stall counter. If that's non-zero, then we have a back end stall. For a front end stall, what we see when we turn variable rate shading on is we see this reduction in overall time between the left hand image here, which is 4.7 milliseconds, and the right hand time, which is 2.6. So that's excellent. That's a really good saving. But what we can see from the blue graph is that we're running far less pixel shader waves than we could do. The left hand graph tells us that we occasionally get to fully saturate the GPU with pixel shader waves, and on the right hand graph that's not happening. And we also see that vector ALU usage is dropping. So while we were hitting 100% quite a lot of the time without VRS, now we're hitting it much less often. And we get this additional warning in pics that vector ALU is starved of instructions. So although we're taking a lot less time, we're not fully utilizing the GPU and its ability to perform math, which is possibly counterintuitive. It's not exactly what we expected. We expected to be pushing these units harder. So, but the really good news is that actually this is an opportunity, because in the case where we're running VRS and we're using less time, we're also using less of the GPU. So we need to be able to fill that to get the maximum benefit from VRS, we need to be able to fill that time with useful work. Fortunately, the solution to this is extremely simple, and it's been around for all of generation 8 as well, which is to use async compute. So when we turn on VRS, we get an immediate profit. But if we want to go and soak up that unused occupancy, we can be running something on async compute at the same time as, say, gbuffer rendering, and that is going to go in and use that additional unused resource. And this could quite easily be something like for ray tracing, updating acceleration structures during gbuffer rendering. It's quite easy to find some kind of workload that you could run at the same time. The other thing we've seen is that you do get a benefit from switching to wave 32 instead of wave 64. That is well worth doing. So I should mention that these bottlenecks, either front end or back end, tend to occur when we have a lot of 2x2 rate. So if you've got a mix of 1x1, 1x2, 2x1 in there, then you're probably good. It's only where you've got a lot of 2x2 that these fixed function bottlenecks can kick in. But of course, that is where we want to pick up the maximum performance. Some early presentations actually on variable rate shading said, really quick and dirty test is to set your whole scene to 2x2, render everything at 2x2, and that'll tell you what the maximum possible performance win is from VRS. And it turns out, in fact, that on Xbox Series consoles, that's not true. You can get even more of a win if you can find some workload to run on async compute at the same time. Something else we've learnt from real titles is that by default, VRS invokes the pixel shader in the middle of the coarse axis. So if you have 2x2 pixels, the actual location that the pixel shader is provided is the center of those 4 pixels. And that's very stable temporally. It'll generate the same result every frame. But in fact, you can get a higher quality if you have temporal anti-aliasing, if you rotate every frame exactly in which of those pixels you invoke the pixel shader. And it turns out we have an extension on Xbox that allows you to do this at 0 cost. So we found that this is very worthwhile in increasing quality. Another tip for that's specific to Xbox Series consoles, where you have a choice of wave width, whether it's wave 32 or wave 64. In fact, wave 64 aligns extremely well with an 8x8 tile size, so we can use cross-lane intrinsics when generating the shading rate, which is a huge optimization. And our shader, in fact, only takes 92 microseconds for a 4K target on Xbox Series X, which is a very small amount of time. It doesn't take very much low-rate shading in the scene to get you 92 microseconds worth of win. So in fact, it's very hard for variable rate shading to be a net loss. It's also true that you can do better than this 92 microseconds. One option would be to put it on async compute and run it at some other time where it can overlap, and you can get that work done effectively for free or at a lower cost. And it's also possible, as mentioned earlier in the presentation, that you might be able to have an existing pass, for example, temporal anti-aliasing, output the shading rate image for free, or again at a very low cost, less than 92 microseconds. One thing to mention is that we have very much focused on tier 2 VRS and the shading rate image, which is natural as this extremely powerful way of driving variable rate shading. But we shouldn't forget tier 1 VRS as well, and being able to mix this into the same scene. And this is where you just say, I want this shading rate for this draw call, whether that's 2x2 for the whole draw call, 1x1 for the whole draw call. And there's a number of use cases for this. So this is for objects which are perhaps occluded by transparency, So if your camera is above water, this could be for everything that's underwater, everything that's behind glass. It could be for reflections, anything in a reflection where you don't, maybe the surface isn't perfectly smooth, it's got some amount of roughness. You may get away with it even for perfectly smooth rendering. Clouds and particles, that's particularly large gains to be had there. As mentioned by Philippine from IdTech, they had a problem with their world's UI objects, which had deliberately very high frequency animating detail that was not reacting well with the shading rate image, so they fixed that using Tier 1 VRS. Full screen passes, it's possible that you might be able to do something at a lower rate. Visibility buffers, where the data that you're writing out is the same every pixel anyway, would perhaps benefit from just being told 2x2 rate blanket. Another area where Tier 1 is extremely useful is where you have, say, your shader is doing testing an alpha value for whether to kill the pixel or not for something like foliage or wire, that kind of thing. So here we would run at full rate because discard will turn off VRS. You maybe do a full rate pre-pass, depth pre-pass, where you're simply writing depth if the pixel passes its alpha test, and then in the main pass you render without doing the test, just set depth test to equals. And typically this geometry is going to generate a high shading rate due to depth discontinuities. There's a lot of depth complexity. Now, if you're just rendering your leaves green, is it enough to say for the depth equals pass, I'm going to render that 2x2 rate everywhere? Or again, as previously mentioned in the talk, you can make your shading rate image depth discontinuity aware. And so that brings us to the end of the content for this talk, and we'll just briefly wrap up with some conclusions. So in conclusion, we've seen some fairly wide-ranging savings from variable rate shading. 10 to 15% does appear to be typical, although it does help more in worst case scenes. And in fact, the overheads that variable rate shading actually is so low, it's quite hard for variable rate shading to actually be a loss, particularly if you have kind of a 2x2 safe area. Universally, we've been told that variable rate shading is actually increasing perceived image quality by allowing DRS to hit higher resolutions. It's causing DRS to kick in less often in the case of Doom Eternal. It allows developers to think about using more of these kind of traditionally expensive effects, particularly volumetric effects. We've seen that async compute is required to get the most benefit from VRS on Xbox consoles. We've seen that VRS can work well with post-processing, and in fact this is where Gears 5 got the majority of its win from VRS being a deferred title. For quality, we should consider using the hardware to rotate pixel center offsets, allowing temporal AA to converge on the ground truth. You should definitely consider something like cone step mapping and parallax occlusion mapping. VRS can very much help give you a win here, where it perhaps couldn't if you tessellated the geometry. And of course, tessellated geometry has more problems with pixel shader efficiency. To date, we haven't seen any titles needing to handle camera cuts in any kind of special way. Titles have not used the velocity buffer for taking that into account when generating a shading rate. As mentioned previously, not picking the wrong shading rate does not give you a wrong result. It gives you a different resolution of results, which is an important difference. We recommend sticking to 2x as the lowest shading rate on Xbox Series consoles rather than 4x. Tier 1 is still important. You can get some benefits there. You can use it to fix problems. If possible, for the highest possible win, you should generate the shading rate after your post effect blurs. And we provide, I think, 3 samples now to help you get going in the fastest possible time. You can, of course, use our shaders and experiment with our samples. And that is it. Thank you all very much for your time making it to the end of the presentation, and especially to IDTech and the Coalition, Philip and Chris, for their great contributions. Thank you.